Crazy Hat Chemist. So another video here, actually a whole entire new unit here on electrochemistry. So let's get started. Bam! So today we are going to give you just a quick little bit of a summary of electrochemistry, and then we're going to move on from there. This is an awesome unit with lots of information in here and applied chemistry. So this is truly applied chemistry, so I have a number of examples of which are showing you how important electrochemistry is. This is the Statue of Liberty, of course, and the Statue of Liberty is made out of copper, elemental copper, and then it is interacting with the water and the oxygen from our environment, and it's forming multiple different copper oxide compounds. And that is characteristic of that green patina of copper, highly sought after. And of course, the Statue of Liberty is totally iconic. Okay, then we have the citric acid cycle. There's electrochemistry happening in that as well. I majored in biochemistry from UC Davis, and electrochemistry is so very important in biochemistry and electron transport chains. Okay, there's just a really simple thing of iron nails in fences or iron anywhere, and it will react with water or the oxygen in the environment just like the copper will, and it will form an iron 3 oxide compound, a ferric oxide compound, and that is otherwise known as rust. And this rust is a non-protective coating, unfortunately, and this is why things that are iron deteriorate over time, especially in the environment without a special coating on it, like paint, for example. This is not hydropower, but electrical power from the wind, and that's also taking advantage of electrochemistry as well. As well as this, these are turbines which are inside the Hoover Dam. Great tour. If you ever take it, please take it. But the same thing is here with water passing through, and it's turning these turbines, which is generating electricity. The same thing is occurring with the wind power and that windmill that I have there as well. Okay, bam. And then, of course, here is a nice little sports car here. Not one that I own, but maybe eventually over time I will. But this is also running on electrical power, and that is a battery operated. Now, we have battery-operated cars entirely, and then we have hybrid cars. So all of those take advantage of electrochemistry. Okay? And then, of course, here's a wonderful example here. This is actually my wedding ring right here with my wife, of course, and it is a platinum wedding ring. And because platinum is a noble metal, it has an oxide, there's no oxide coating on this because it doesn't react with the oxygen in the environment or the water environment, unlike the copper or the iron that I aforementioned here. So gold, doesn't react with the environment as well, same with platinum. All right, so these are many examples of why electrochemistry is so very important to us. So let me get into some of the nitty-gritty of this. So I've got two rectangular boxes here. So Leo is the loss of electrons is oxidation. So Leo the lion, hopefully you're going to remember that. Leo the lion. What does a lion say? Grrr. So Leo the lion says grrr. So Leo is loss of electrons is oxidation. Okay, and an increase in the oxidation number is characteristic of oxidation. So we're going to be using this in just a little bit. An increase in the oxidation number is oxidation, and this is also called the reductant. Okay, the reducing agent, which is an electron donor, is oxidized. Okay, and the anode, which is negative, this is where the electrons leave from this point and then go to the cathode. Now, I'm hoping that you remember that electrons are negative, and that's why the anode is negative. Okay, and electrons emanate or start at the anode, which is the negative component or the negative part of a battery. We have a positive end, we have a negative end. The anode is the negative end. Okay, and anodes decrease in mass. Well, look at this. Take a look at this. The anode is negative and it decreases in mass. So when you have a particular type of cell, which we'll discuss in just a moment here, that metal is decreasing in mass, it's dissolving. So anytime you hear that the metal is dissolving, you know that that part of the battery or the electrochemical cell is the anode portion of it. Okay, now we've got Leo the lion says what? Grr. So Leo the lion says grr, and grr is the gain of electrons, that is reduction. And notice that the word red is in reduction. I'm hoping that you tie those two things together, as well as noticing that reduction is a decrease. So that means that a decrease in oxidation number is characteristic of the reduction half reaction, and it's also called the oxidant. Okay, there's a lot of vocabulary in here. Okay, the oxidizing agent is the one that's being reduced, and that is also the electron acceptor. Okay, and the cathode, which is positive, that's where the electrons go towards. So electrons, which are negative, start at the anode, and then they are negative, so they start at the anode, and then they move towards the cathode because electrons are attracted to positive things, and therefore they move towards the cathode. Okay? And of course, because the cathode is positive, that means, and that hints at that the cathode is going to increase in mass. And this is when you plate on a metal. So if you have like really inexpensive metal, like relatively inexpensive metal, you could actually use iron, you could use copper, okay, and then plate on top of that another metal like gold. And you could have a gold coating plated on top of copper, and it looks like gold and doesn't quite totally behave like gold, but it looks like gold. So you wouldn't even know the difference by just looking at it. Okay? A galvanic cell, which is otherwise known as a battery, is a spontaneous reaction, whereas an electrolytic cell requires energy. So that's where we're plating on a metal. And we use the plating process for a variety of different reasons, and I'm going to show you many of those different reasons as examples within this entire unit. So watch all the rest of the videos. Okay, electrons flow from the anode, which is negative, to the cathode, which is positive. Anode, negative, decreasing in mass. Electrons start and emanate from that point and move to the cathode, which increases in mass. All right, okay, and when we talk about redox reactions, we are really talking about reduction, oxidation reactions. So redox is a shorthand notation of a reduction, oxidation reaction. So that's what we're going to be talking about. Okay, so we're going to tie in some prior knowledge that we should have known before, okay, and that prior knowledge is going back to that acid-base chemistry unit where we did titration problems and whatnot, calculating the pH, the hydronium ion, hydroxide ion. Okay, and so here's this generic equation of the dissociation of an acid. It's going to be a weak acid because I got that equilibrium arrows right over there. Okay, and the acid, the HA, is the weak acid on the left-hand side, the reactant side, and its conjugate base is on the right-hand side. That's the A1 minus with the decrease in the number of hydrogens. And the acid is a proton donor, therefore the hydrogen ion. So we're going to correlate this with a little bit of electrochemistry. Now in electrochemistry, we have oxidation reduction reactions. And just like in acid-base chemistry, we have to have an acid and its conjugate base, or a base and its conjugate acid. So we're going to have those two things tied in together here with electrochemistry. So here's an electrochemical reaction. This is actually a half reaction. We're going to be using this in a balanced equation here pretty soon, okay? But we're going to label some of this. So the copper, that's a solid, has a 0 oxidation number charge, and it's being oxidized. And the reduced is on the product side. That's that 2+ ion of copper that's aqueous. Okay, the oxidized is the electron donor. Okay, so that's tying in some of that prior knowledge of acid-base chemistry with these conjugate pairs and oxidation reduction. With oxidation, you have to have reduction. With reduction, you have to have oxidation, just like an acid and its conjugate base, or a base and its conjugate acid. Okay, fantastic. So just to have another little information to plug in here so that you can stand on something for this entire unit. And here is a story of an ox and a red cat. Now it's an ox, like oxidation, okay, anode. And a red, of course, reduction, and a cathode, okay? So red cat, cathode, and reduction go together. So there was once an ox and a red cat. Both wanted to live on an isolated oil rig, but there was only one remaining. The ox and the cat flipped a coin. Sadly for the ox, it lost because it's oxidation, and it lost. So the ox became sad and negative, of course, because it's negative, right? Anodes are negative. And consequently stopped eating, losing mass, because anodes lose mass, and they're negative. That's why they're negative, because anodes lose mass. Meanwhile, the cat said, "Grrr, I'm so hungry. There is no food on this oil rig. I'm going to eat you." The cat was reduced to eating the ox, which of course made the cat fat, gaining mass. Okay, there's an ox, and of course oxes have these pointy ends on the horns, and those are most certainly negative. Okay, there is a red cat, and what do cats say? Well, they say grr, right? And of course cats are always positive because they're positive. Okay, and there is an oil rig. So an oil rig is oxidation is the loss of electrons, reduction is the gain of electrons, and that's why it's an oil rig. And this is why this little story happens on an oil rig. So if you remember this story, then you can correlate what's happening with the oxidation half reaction and the reduction half reaction. That's the whole point of this entire story. Hopefully you enjoyed that story. Okay, so here's a little bit of a summary of some electrochemistry math and equations that we're going to be using in this unit, because this is a very important unit here. So number one, we're going to be looking up a table in the back of your book in an appendix, and we're going to be finding reduction half reactions. With those reduction half reactions, we're going to be using this equation, and that's the E naught for the cell. Just remember that zero. That superscript 0 is read as a naught. We've read that before. So E naught for the cell is equal to the E for the reduction, or the cathode half reaction, minus the oxidation, or the anode half reaction. A key to this equation is that you never multiply. That's one of the most common errors for students to make, is that you never multiply when using this equation. And that applies to the balanced electrons that are canceling out. So do not multiply while using this equation. Just do the straight subtraction from the oxidation half reactions, which is in the appendix of the back of your textbook. Okay, and then we have this equation right here. E is equal to the E naught minus RT over NF times ln Q. And this is called the Nernst equation. So we're going to talk about what each of these individual components deal with. R, of course, is the gas constant. T is the temperature. N is the number of moles of electrons that are transferred. F is Faraday's constant. Ln is the natural log. Q is the reaction quotient. That's products over reactants with the stoichiometric coefficients as exponents. E naught for the cell, well, that's under standard conditions. And so the E on the far left-hand side, which this whole entire thing is equal to, is the volts of that cell, or that electrochemical cell, under non-standard conditions. So this is why it's non-standard conditions, and that's why it's Q and not K. All right, this is Faraday's constant, and we're going to be using this quite a bit in this unit. Faraday's constant is 96,485 coulombs per mole of electrons. So that's generally a constant you need to memorize, or it's somewhere in your book, guaranteed. You need to know this correlation here, and joules is equal to coulombs times a volts. We already got what our coulombs per mole is, and that's a Faraday. Well, joules is equal to coulombs times volts. So we're going to be using this to convert from coulombs to joules with the product of the coulomb volt there. Okay, then we have this equation, which is a new equation for us, and we already talked about entropy and enthalpy and Gibbs free energy. Delta G naught is the Gibbs free energy. Okay, that's equal to negative NF E naught. So delta G, Gibbs free energy, is equal to negative N. N is the number of moles of electrons that are transferred. F is Faraday's constant. E naught is the electrochemical cell potential under standard conditions. Now, we also actually use this equation in that thermodynamic unit, the second thermodynamic unit. Now, what I've done here is I've flipped this around. Typically, the delta G naught is on the left-hand side, and it's equal to negative RT ln K. Okay, but what I've done is I've taken the delta G's, put them flanking on either the left or the right-hand side, and so what we're going to notice here that delta G is equal to two different things. So what we can do is substitute in what delta G is equal to, and now we have two equations that are equal to each other. So we have this equation here, which is very important. It's a combination of these two equations, and on the left-hand side we have negative NF E naught is equal to negative RT ln K. So we can correlate this with the E naught for the cell, the reaction quotient, or the equilibrium constant K in this case. Really important set of two equations. Okay, so the other thing that you need to remember for this entire unit, and this is correlating the thermodynamic unit together with the equilibrium unit and the electrochemistry unit, and that's why this unit is so very important, and it's time and building in previous units. So the equilibrium conditions, we have E naught for the cell at equilibrium, that's equal to 0. Delta G naught for the cell, that's equal to 0 under equilibrium conditions, and the K, that's the equilibrium constant, that's equal to 1 under equilibrium conditions. So you should know equilibrium conditions here. Now, when it is spontaneous or product favored, then we know that E naught for the cell is going to be greater than 0. That means it's going to be positive. Okay, the delta G naught for the cell is going to be less than 0, therefore it's negative for a spontaneous reaction, and the equilibrium constant K is greater than 1, and that means it's product favored. Of course, from this information right here, you should be able to get the non-spontaneous versions that are reactant favored, and you're just going to flip that sign, essentially, on these. Okay, hopefully that works out for you. I am the Crazy Hat Chemist, and we cannot end this video without a crazy hat, and so I am totally bull about chemistry. I'm not an ox, but it's the best I can do here. It's a bull. Don't forget to subscribe to my YouTube channel. Give me a thumbs up on this video here, please, for me. Subscribe to my YouTube channel. Look me up online, and you can always donate to my website. You can get yourself a cool sticker or a cool t-shirt. My website is on the back of the t-shirt. I am the Crazy Hat Chemist, and I hope you have a fantastic day. I'll see you next time for another cool chemistry video on electrochemistry. Bye for now.